Today what we're going to be focusing on, and again I apologize for being a few minutes late. Today what we're going to be focusing on is motion in more than one dimension. So we have done a lot of kinematics of what has been 1D motion with constant acceleration. And this week we're going to focus on what happens if you move in two directions, 2D motion, and we're going to stick with constant acceleration. And to do this, as I said, we started it at the very end of yesterday, and the online quiz kind of reviewed the key elements of vectors. But we're going to just briefly go over those addition rules and the addition properties of vectors, because that becomes even more important in 2D than it does in 1D. But a lot of the ideas we went over about catching things, having a delay, having two objects move versus having one object have two different motions. All of these basic physics are still important and still apply in two dimensions. So we're just building on that. So that'll all come back. Any questions on that? As with 1D, you'll see for most of these problems, there are at least two ways I do it. So when the solutions get posted, you'll see one that focuses on drawing the vectors, what we call the graphical solution, and one that focuses on using components. So again, find the mode that you're most comfortable with and use that as you go on. Choose from those. At the heart of everything we're dealing with an equation like this. And as I mentioned earlier, this has two pieces to it. One are vectors are multiplied by numbers. So you have to remember what that does. So if I have V naught and then I multiply it by time, that just makes it longer. But it keeps the direction the same. What is the only number I can multiply by, or type of number that might change the direction of a vector? Negative. What does the minus sign do? Just switches the direction. So I do have the situation where multiplying by any negative number would reverse it. And you have to keep that in mind. The other feature of this that we highlighted is the process of adding two vectors. So we do have to add two vectors. We've done it a lot in a lot of different ways, but now we're going to actually summarize it all in a nice formal picture. And we're going to do it for two dimensions. As I said earlier in the class, the real world is 3D, right? So you have to worry about x, y, and z normally. But everything we do, because it's easier to draw on a piece of paper, we do in 2D, because a lot of motion is just in 2D, so it works. And also 3D is a pain to draw and it's harder to work with, and it's basically the same. So it doesn't really make much sense to do it. Now, if I'm going to add two vectors, so there's vector A, there's vector B. There might be some angle theta between them, and they equal vector C. One thing you could do, if you were really good with your triangles and trig, you would remember that the length of C equals a squared plus b squared minus 2ab cosine times that angle theta right there between them. This looks a lot like the Pythagorean theorem. Because, does anyone remember what the cosine of 90 is? 0. So when that angle's 90 degrees, this goes away, and you have the Pythagorean theorem. This can be a useful shortcut in many problems. It's called the law of cosines. We also have the fact that the sine of theta divided by c, if I add in an angle alpha, is the sine of alpha divided by b. This is our law of sines. Now, I put this up here. I want to be clear. I am putting this up here if you feel really, really comfortable with geometry and trig. If you don't, and this makes you nervous, don't even write it down. But I do want to point out to people that this can be a very useful thing if it's something you're comfortable with. You might say, well, why am I showing it to you? Well, some of you will want to use it. Now, the more useful and common thing to have happen is we have some vector A that we're adding to some vertical vector B. Because remember, these are our common two vectors to use. And which direction is G? G points where? Straight down. So it's vertical. So there is, very often in our problem, a right angle that's related to something important in the problem. Maybe the distance we traveled. And often, you know this other distance, so you can figure out this side, say, is b minus h. And I went through on Friday, so I'm not going to repeat it here, how you can use sine, cosine, and tangent in this situation. And so this is actually a very powerful, and I would argue very useful thing for you to review. And if you can get comfortable with it, it will really help you a lot with the problems. And so to help you with that, like I said, on the information webpage is a PDF called Kinematics Review. And I go through in detail how to use this. I'll also do it in all the example problems I tend to do this week. So it'll really help. Any questions on that? We ended it kind of quickly on Friday, so I just want to check. Now, the more common thing that most people have learned about are components. So you make an x and a y axis, often called I hat and j hat, and we'll see how that's used in a minute. And you have some vector A. And we break it into the components AY and AX. Notice our components really are, strictly speaking, vectors. The vector A is the sum of two vectors, the vector in the x direction and the vector in the y direction. And we write these as AX times I hat plus AY times j hat, or we write them as a pair, AX, AY. And these numbers here give us the size or magnitude of the component. And also, by convention, they have the plus or minus sign for the direction along the axis. So let's be clear on all the different pieces, right? Notice from the way I drew the picture, this is just our standard vector. Oh, that's an x. It doesn't look like it. Vector addition. We went head to tail, and then tail to head, and we got the vector A. And we write it in this notation where the I hat and the j hat are vectors in the direction of the coordinates. So strictly speaking, these are still the vectors right here. And then the other way we can write it as a pair of numbers that are our two coordinates. So there's a lot of different notations you'll see in the book or in different situations or tests you have. And what I'm going to do now is a couple of demonstrations here to let us know why it is these components can be used and why they're even useful. So we open with a clicker question. Now, we have a demonstration here. And what's going to happen is when I pull this string, this little thing will fire. Okay? And it will shoot out the ball that is sitting here. So there is one ball that will be sitting here. And that will launch the ball in that direction. So it'll be kicked horizontally, and it'll have some initial horizontal velocity. That is the horizontal ball, answer A. This ball is just sitting here. So notice as it fires, this pin disappears, and this ball will just fall straight down. And you'll be able to tell when they hit by the sound. Yeah, I didn't want to scare you, so that was a preview. And the question, yes?
Are they released at the same time?
They're released at exactly the same time, or as close to exactly as we can come with our clever device, right? And so the question is, which hits the ground first? The horizontal one, the one that's dropped? It depends how fast the horizontal one is thrown, or they hit at the same time. About half of you are going for D, because of course everything always happens at the same time, right? I mean, you've learned your lesson if you've been paying attention in the class. Some of us think it depends on the speed, and a few, the ball dropped first is going to hit. So let's actually do this demo. So again, the key here is to listen carefully. Whoops. So if you notice, you hear only one smash. Okay? So they hit at the same time. So that, keep in mind, whoops, got to click on it. They both hit at the same time. Now what I'm going to do is attempt to reset it, where I will launch the ball up at an angle. This is a little more challenging. This version doesn't always work. But now ask yourselves, which is going to hit at the same time? Or is one going to hit first? Apparently I can't bend over today. I lose the microphone. Is one going to hit first, or is the other one, or are they going to hit at the same time? So let's get this set up while you think about it and vote. Okay, everybody's going with the ball that's being dropped first pretty much. Okay, as I said, you have to listen carefully. What you're trying to hear is two separate hits. It's easier for me, I'm standing right here, but this one does hit a little before that one. I don't know if you believe me. Yay! Success, physics at work. I'm going to try it one more time where I see if I can tilt it even more.
Look under the table.
Well, no, it's not this. I can tilt this. It's whether or not these things will fall off if I tilt it too much. And they're not, notice it's a little bit hard because they're not really quite at the same height, but they're close enough. And now you should have really heard the difference. And that difference really was not from the slight difference in height. So what is going on in these two examples? What we want to see is the following features, okay? And we can easily draw it. Now, the first one, we have a situation where we have two balls starting at the same height, and they're going to land at the same position. So this is some height. So they're starting at the same height, h, and the only difference is one of them has v naught equal to 0. And the other one has v naught in a horizontal direction. So if I want to draw the displacement vector diagram, right, I have to draw these two vectors added together to give me this. Well, this one is simple. It just has 1/2 g t1 squared, however long it takes to fall. This one over here has v naught t. Notice t can't do anything to the direction of v naught. It just makes it longer. And this is t2. And it has 1/2 g t2 squared. And this is delta x for that ball, ball number 2. Notice, without actually having to do any algebra per se, you can see immediately that this vector has to equal this vector because they both equal the height h. And so there is no choice but for 1/2 g t1 squared to equal 1/2 g t2 squared. And I can cancel all of that, and I see immediately that t1 has to equal t2, so they have to hit at the same time. Make sense? What I want you to do now is take a minute, draw the same picture for the case where the ball is launched up at an angle, and decide whether they should hit at the same time or different times. And if you need to talk to the person next to you, go ahead and do that if you're not sure how to draw it. Would anyone like to volunteer a picture? Or are you all caught up on Facebook now? Anyone want to volunteer a picture? Well, what should the V naught look like for this ball over here? What should I draw? Everybody put your arm where V naught should go. Excellent. And so, of course, that is also the same as V naught t. Now, where do all my 1/2 gt squares go? They go down. Now, here's the key. This is what makes drawing these pictures so useful. 1/2 gt squared has to start at the end of V naught, which in this case is 0, so it's right where I am. And it has to end where we land, because that's what delta x is, right? It's x final minus x initial. And so V naught t plus 1/2 at squared has to end up being the same as that vector. So the head of a t squared has to end up at the endpoint of delta x. So if I come over here for the V naught t, I have to draw 1/2 gt squared from here to here. So this is t2. I have to go from the end of V naught t, because that's what I'm adding it to, and I have to end where delta x ends, and I know it ends on the ground. So already from drawing the picture correctly, without any numbers, right, I know that 1/2 gt1 squared is less than 1/2 gt2 squared. just look at the lengths of the vectors. That one's h, and this one has to be bigger than h by some amount x. And therefore, when I cancel everything out, T2 is bigger than T1. And so the one shot up took longer to fall. Again, I didn't need to do any algebra. I didn't need to know any numbers, and I found out that this was true. Any questions on that? That is understanding that piece, how to draw 1/2 gt squared relative to v naught t and delta x, will save you a ton of time in these kinematic problems. It'll really be helpful. Yeah?
Are you saying that no matter what the horizontal velocity is, the initial velocity, if there's no angle, they should at the same time?
Exactly. Notice here, there's absolutely no impact of v naught. There's no way it can, because this, by definition, has to be h. V naught is containing no part of h whatsoever.
Like a bullet shot out of a gun?
The bullet will hit the ground at the same time as you drop a bullet, as long as you fire it horizontally. It'll just land very, very far away. Yeah. And actually, I bet you, if you look, you can find videos of YouTube that show that. You have to do some fancy stuff. And this may not be right, but I think even Mythbusters did that once.
Yeah.
I believe, right? Yeah. So there's even a Mythbusters episode. It takes better equipment than we have, and they don't let me shoot guns. So that's how things have changed. When I was an undergraduate, there was a demo with an actual gun being shot into a piece of wood. And there was a nice piece of glass between us and the demo. Yes?
So we're assuming we can't shoot anything horizontal fast enough to achieve orbit?
Well, even if so that's an interesting question. If you shoot it fast enough horizontally so that it goes into orbit, it's, how to think about that? Then the assumption that they hit at the same time relied on the ground not curving, right? As soon as it goes far enough that the ground curved, then I have to draw a different picture, right? Then I'm drawing 1/2 gt squared like that, and I'm drawing v naught t and 1/2 gt squared like that. Okay, and yes, this now takes longer to hit because it misses. But that has to do with the fact that I have to draw different ground. And so yes, the answer to your question is, by drawing the ground flat, I've assumed it's not going so fast that the Earth curves any amount. Good question. And again, that's where these pictures are so helpful. The pictures actually let you know what you're assuming, what you're doing, what you're not doing. Any other questions? Excellent. We can go to clicker question 3 now. What I have here is my rocket launcher. It launches my vertical missiles, so the ball will be launched vertically. The way it'll work is when it gets here, it releases the switch, and the ball gets launched straight up. The question is, where will the ball land? The cart's going to be sliding along at constant velocity. It's going to pass that point. And the question is, does the ball being launched vertically land in the cart, behind the cart, in front of the cart? And it depends on on the speed of the cart. Did I start the clicker question? No, I did not. So let me start it. We have a pretty solid voting block today. 50% of you went within the cart. So let's see what happens. Magic! Now, this is riskier because there's a little bit of air resistance. I will try it a little bit faster. Ah! Notice it landed in the cart. It just then bounced out. Sort of like my putting. Ah. But the main thing both times, no matter how fast I went, it landed back in the cart. Now, this, again, we can get from drawing the pictures. It's a little bit harder. So let's think about these pictures for a moment. The one that's easy to draw is the cart. It's just moving with some velocity, c, in the horizontal direction. So its displacement is vc times t, because the acceleration of the cart is 0. Now, how do we think about the ball? Well, first of all, we do have to recall, it's helpful to recall in this case, frame of reference. I showed you what the ball was doing relative to the cart. And remember, constant velocities, we said we can't tell. Everything has to be the same no matter what frame of reference we use. And the frame of reference of the cart, remember the cart's velocity is now 0. The ball moves straight up. So the only thing it can do is fall back down. So in the frame of reference of the cart, the ball lands in the cart. And this is a central piece of physics. If you are dealing with constant velocity frames of reference, the physics answer can't change. And so if I have a collision in one frame of reference that the ball lands in the cart, then we all have to agree that the ball lands in the cart. So even though you see the cart moving, since it happens from the cart's frame of reference that the ball lands in it, you have to decide the ball lands in the cart. So what does that mean? Let's look at it from our frame of reference. In our frame of reference, the velocity of the ball is at some angle. So it has velocity of the ball times time. It has 1/2 gt squared. And this delta x of the ball has to equal delta x of the cart. And it gets launched at some angle theta. Notice the various physics we used in this situation. Right here, we used a collision means same position. Now when I write down over here, delta x of the cart equals v of the cart times t equals, and I look at my picture, vb of the ball times t times cosine of theta, which is delta x of the ball. The fact that I use a single time comes from the fact that I have a collision, which also means same time. Notice there was no delay here, there was no waiting, there was no anything else, right? The ball got launched at the same time I have the cart going, and they land in a collision, so it's the same time, same place. So unlike my first demo, notice here I had a T1 and a T2 at the beginning because I didn't know if they were going to hit at the same time or not. Right? They're hitting the ground at completely different places. There's no collision, so I don't necessarily need same time for them to hit the ground. Here, I've determined by using this frame of reference that the ball landed in the cart, therefore I have a collision, and therefore I can write this equation. That is a central piece there that will come up over and over again in these problems. So you really want to be aware of that. And this highlights the idea of what we mean by a component to the velocity. notice we can write these equations as v of the cart times time, and we can write it as vb cosine theta times time. And we call this the x component, or horizontal component, when I make my coordinate system. If you're going to use components, you better have drawn a coordinate system. If you use components and you don't draw a coordinate system, you will lose points. Because this only makes sense because I drew that. Yes?
I have a quick question. How did you do the VB of the t times cosine theta? How did you
This is just, I have a right triangle because I know G is always perpendicular. And once I have a right triangle, this side is my adjacent angle to theta. So, oh yeah, that's an x. You know what? Let me quickly review that in a bigger piece of paper. I did this really quickly on Friday, right? But we will often have the adjacent, the opposite, and the hypotenuse. And you learned it as cosine theta is adjacent over hypotenuse. Sine theta is opposite over hypotenuse. The most common way we're going to be using it in our physics problems is we will know this, and we will know this, and we want to know that or that. And so it's useful to rewrite each of these as the adjacent side is the hypotenuse times cosine theta, and the opposite side is hypotenuse times sine theta. And to remember this form of it versus that form. Now, if you don't remember this, but you remember this because that's what you learned so long ago, then just do the two steps. Now, some people make the following mistake. They assume that this is an equation for the x component, and this is an equation for the y component. And then you'll be doing a problem, and you'll have an x angle and a y angle, and this will be theta. And it'll be next to the y-axis. This always works. This doesn't always work. This won't work in this case. So that's just kind of a warning. Did that help? Any other questions on this one? So the big final message of all three demos, whether you realized it or not, is that components of perpendicular coordinates are independent. So that if I have an x and y axis, and I have some vector A, and if that's my angle theta, then AX equals the magnitude of A cosine theta, AY equals the magnitude of A sine theta. And I have another vector B with the same sort of thing, and I want to make C. I can do the x direction. I can find CX is AX plus BX. And in the y direction, I can do CY equals AY plus BY. And that'll give me the vector C, which is CX I hat plus CY J hat. So I can do it in this traditional component way, in addition to just looking at the trig. And there's some times where this is actually a little bit faster. Either you already know the components. Notice in this case, all I cared about was the motion in the x direction once I picked x and y. And so just using these components is an easy thing to do. So as you go through the examples this week, we're going to start one now, and when you get to discussion section, one of the main things this week is to decide for yourself, which are you more comfortable with. Do you always want to just use components, where you'll see you have to really keep careful track of minus signs and do other stuff? Or do you want to draw the picture and just use the trig straight from the picture, where you have to be really careful to draw the picture right and use your trig? So there's pluses and minuses of both, and depending whether you're more graphical and geometric or more algebraic, you'll like one more than the other. Any questions? So our problem. Oops. We're going to throw a ball off a 30-meter high cliff with an initial velocity at an angle of 30 degrees, and we're going to ask, where does it land? So we draw our picture. We have a 30-meter high cliff. We're going to throw the ball. It's being launched with a v0 of 25 meters per second at an angle of 30 degrees above the horizontal. And we're going to ask, where does it land? So this one is about as standard and as straightforward and simple as they come. Couple of things to keep in mind as we draw the various pictures, and I'll do it here. Notice this vector is delta x. Right? It starts from x initial, our initial position, and it goes to x final, our final position. Notice there's some angle here for delta x. I'll call it theta 1. But also notice that we land with this final velocity. The velocity, if you recall when we defined it, and this is why it's important to remember your definitions, is tangent to our trajectory, right? It was the derivative of x with respect to time. So it's the slope of this curve we're making. Notice the angle we land at, I'll call it alpha, does not equal theta 1. This is very important. These are the sort of things that you have to get used to from the English point of view. If I ask where it lands, I'm talking about displacement. If I ask what angle it hits the ground with, what am I talking about? Displacement or velocity? Velocity. Velocity is the direction you're moving, so velocity is the angle you hit things with. So if you want to know what angle you're hitting something with, if you want to know if you're going up or down, any of those sort of things, that's velocity. You might need to use the displacement equations to solve the problem, but you're ultimately going after velocity then. And that's really important to keep these two angles separate in your mind. Any questions on that? So let's set up this problem. We're going to start, since we want to know how far it goes, that's part of the displacement vector. So that's what we're going to draw first, is this vector equation. And to draw it, we have a v0 t. Remember, 1/2 gt squared is always vertical. We know this is 30 meters. So we can make a right angle here. And we know that this is 30 meters. This is what we want to find, the distance d that it goes. And we know this angle is 30 degrees. That also tells us right away that right in here, we have 1/2 gt squared minus 30 meters. And now we pretty much have everything we need to solve the problem. If we look right here, we see that this side, d, is just v0 t cosine theta. That's what we did earlier. The cosine of theta is adjacent d over hypotenuse, v0 t. So this I know, this I know. If I can find t, I'm done. And notice if I look right up here, I know this, and I know that. So I also know tangent of 30 is 1/2 gt squared minus 30. The opposite over the hypotenuse, v naught t. Oh, I even know that. Sorry, tangent. I lied to you. Tangent is opposite over adjacent. So that's over 30. Why did I pick opposite over adjacent? Because I only have time in the numerator. Right? If I did sine, what I started to write was sine of 30. And that has a t in the numerator and the denominator. Makes the algebra a little harder. Okay? So tangent's opposite over adjacent. Now I have an equation. This will give me t. And once I have t, I can plug in here. So I'm going to just write that down for you.
Adjacent is what we're looking for.
Oh, I'm sorry. Oh my gosh. I clearly have not had enough sleep this weekend. I got adjacent because I confused myself and looked at my picture, not my notes. So I'm glad someone is awake in this class, and it's not me. So let's hop over to sine and do the harder version of the problem. I still know everything here. Ignore everything I said about that. When you get, I was just testing you. That's what we do all the time. So we ignore that. I could have done it the other way, and it just would have been even harder. So I have the 1/2 gt squared minus my v naught t sine. See, I would have known right here when I started copying from my notes that sine shows up. Minus 30 meters equals 0. Notice I have a quadratic formula. I get t equals minus 1.5 seconds and 4 seconds. So which one do I use? 4 seconds, because I want when it lands in the future. I plug that in here. And I get out a distance of 86.6 meters. What I'm going to do is I will do this again correctly with components on Wednesday. And we're going to ask the other question, which I want you to see if you can answer before Wednesday. What angle do I land at? See if you can answer that before Wednesday.